My name is Christina Wetzel, and this is Lab 5, Magnetic Braking and Faraday's Law. This lab report has four main parts: the introduction, a summary of the physical data, the computer calculations, and the conclusion. In the introduction, I will review the overall purpose, principles, and results for this lab. In the physical data section, I will go over the procedure, detail my tinfoil measurements, and summarize my experimental results. In the computer calculation section, I will go through my code and generated model to explain the results and the process. Finally, in the conclusion, I will analyze the reasonableness of my results and answer some theoretical questions. The purpose of this lab was to collect observational data of a magnet falling through a non-ferrous tube and to model the same situation on a computer in order to compare the results. The physics principles used in both the physical experiment and the code are Faraday's law, which helps us find EMF from flux, the Biot-Savart law, which allows us to calculate magnetic field, Ohm's law, which is EMF is equal to IR, or current times resistance, Newton's second law, force is equal to mass times acceleration, and Newton's third law, that every action has an equal and opposite reaction. The results for both portions of the experiment are shown here in the lower right. The procedure for this experiment was relatively simple. After obtaining the materials required, I first used the Tessimeter app to determine which end of the magnet is north. I then marked the magnet accordingly and measured the length, radius, and aluminum width of the tube. Finally, I took a video dropping the magnet through the tube, measured the time it took to fall with a stopwatch, and recorded the data. I repeated this experiment 5 times and took the average at the end. My tinfoil measurements for this experiment are shown at the bottom of the slide. Shown here is my data for this experiment, with the average at the bottom being my final result. I observed the magnet falling through the tube much slower than it would have in free space without a tube. For the coding portion of the lab, I started by defining constants to be used throughout. The code shown here then sets up parameters for the graph to be displayed, sets up the geometry of the tube, and creates the tube by establishing many small rings with the appropriate physical properties of aluminum and appending them together. This portion of the code defines the properties of the magnet used and creates the magnet overall. Additionally, the code initializes the magnet's velocity as 0 and defines a function dipole B that finds the magnetic field of a magnet at a particular location. This portion of the code defines a function that will calculate the derivative of flux with respect to time, or EMF, using an equation from the derivation of the Biot-Savart law and Faraday's law. It then forms a while loop that will simulate the magnet's drop through the tube and calculate the time the magnet entered and exited, finds the gravitational force on the magnet using Newton's second law, and uses the earlier defined EMF function and Ohm's law to calculate the value of current in each ring. Finally, this portion of the code changes the color of the ring to show current direction and magnitude, computes the typical B field at each ring in order to find the force on the magnet by the ring, and finds the net force on the magnet. It then updates the magnet's position and velocity based on the net force, updates the graph, and prints the total time that the magnet took in the tube. Shown here is the graph and model midway through the drop generated by my code. In the model, the red portion represents clockwise current and the blue represents counterclockwise current. We know this because with a downward-facing dipole, the bottom of the magnet experiences an upward change in magnetic field over time, as the magnet gets further away from the observation point, which leads to clockwise current. While the upper part of the magnet experiences a downward change in magnetic field over time, as the magnet gets closer to the observation point, leading to a clockwise current. Flipping the magnet around would theoretically reverse these colors with the same time result, as the magnetic dipole would face the other way, but all of the magnitudes would stay the same. Additionally, the velocity versus time graph goes flat for a portion of time, indicating that the two forces on the magnet, the ring force and the gravitational force, must be equal and opposite each other. As by Newton's second law, if acceleration or the slope of velocity is 0, net force must also be 0 on the magnet. The number printed at the bottom of the graph is the computer simulated result for this experiment. In conclusion, while both of my results were reasonable, they were quite different from each other. Experimentally, this may have been due to the fact that my tinfoil was thin and my magnet is a little bit beat up. However, the lab code also models the tube as many individual rings and does not take into account the continuing effect of each ring on the magnet after the magnet passes it. The code also does not account for friction against the tube, and these things may make the code more accurate if incorporated. To answer theoretical questions, we can't use a ferrous tube in this experiment because the magnet would stick, as ferrous materials are magnetic. If the resistivity were as close to 0 as possible, the current value would increase, which would increase the force on the magnet, slowing its fall even more, possibly even moving it in the other direction. Finally, if holes or slots were cut into the tube, current would not flow in those areas, as current can only flow around a closed path, and the magnet would fall faster through the tube, as no current means no induced force. Thank you so much for watching.